Hello everyone. In this video we are going to study about the differentiator, which is one of the application of an operational amplifiers. Our operational amplifier can also be designed to work as a differentiator, where let's have a look at the differentiator circuit and how this is going to generate as a differential output. A differentiator is a circuit in which the output voltage V0 is proportional to the time derivative of the input voltage. That is, it states my V0 is proportional to the time derivative of the input voltage. That is, V0 is equal to with some constant dV in by dt. So that is what your differentiator is going to perform that task. So always remember, a differentiator is a circuit which is going to produce the output voltage, which is nothing but it is proportional to the time derivative of the input voltage. Now when we look into the circuit of the differentiator, we have an operational amplifier. To this operational amplifier, for the inverting input, we are going to connect a capacitor instead of a resistor, and we are going to connect the input. Remember, whether it could be a differentiator or whether it could be an integrator, we are going to connect our input to the inverting terminal and my non-inverting terminal is grounded. Now after this, when we look into the integrator, our feedback element was replaced with capacitor, but in our differentiator we are going to have our feedback resistance as it is, but the capacitor is replaced in the place of series resistance. The only difference between your differentiator and the integrator is the place of the capacitor. The capacitor is used as a feedback element in the integrator, but here in differentiator the capacitor is used in the place of a series resistance. Now with this application we can have a look at what the differentiator is going to do. The differentiator may be constructed from a basic inverting amplifier. So if an input resistor R1 is replaced by a capacitor C1. Now let us have a look at the output voltage that your differentiator is going to produce. As of in the integrator, we came to know our output voltage V0 was directly proportional to the negative integral part of, that is, let us have, so for the integrator we came to know that the output voltage V0 was directly proportional to the negative integral part of the input voltage V in and inversely proportional to the constants R and C. But when we come for the differentiator, we don't know what is actually the V0. So let us first find out the output voltage for the differentiator. In differentiator, we have, let us apply the KCL at node V1. So we have the point here, or the node which we call it as V1. Now let us apply the KCL for this node. We know our current is going to branch across these two. So my I1 is going to branch as IF and IB. where IB is equal to 0 when we apply the virtual ground concept. We already know IB equal to 0, and we know it is V1 is equal to V2 is equal to 0 from the virtual ground concept, which we have discussed in the previous videos, right? So let us apply KCL for the node V1. So when we apply the KCL for the node, it states that number of currents entering the node is equal to number of currents leaving the node. So as a result, my I1 is equal to IF plus IB, where IB is equal to 0. As a result, I can say my I1 is equal to IF, right? So my I1 is nothing but my IC. We know we know the current expression in terms of C, that is C is C into dV by dt. So apply what is my find out what is I1. I1 is nothing but C into dvi minus dv1, or I can take a common divided by dt, which is equal to what is my if. If is nothing but v1 minus v0 divided by rf. So this is what is the expression that we are going to get for if. Now once we get it, let us find out. We know our v1 is equal to v2 is equal to 0. So as a result, I can say d into dv1 is equal dv1 dv1 is equal to 0. So as a result, I can say dvn divided by dt is equal to v1 is 0, somehow my output, that is minus v0 divided by rf. Now I resolve this for the output voltage V0. V0 is equal to minus R into C dVi by dt. So this is what is the expression for the output voltage of the differentiator, which is one of the application of your operational amplifier. We have seen many so far. We have seen in many. So far the whatever the videos we have seen many of the applications like summer. That is, it could be an inverting summer, whether it could be an non-inverting summer, subtractor, integrator, differentiators, and later on we'll be looking into the followers, voltage followers, and comparators. So for all this, we have the output voltage expression, and we also have the gain expressions. Now coming to the differentiator expression, we can get from this expression we can get the inference as the output voltage V0, the output voltage V0 is equal to R into C times, that is whatever the constants we have, that is the value of the resistance and the value of the capacitor with respect to, that is equal to R and C times the negative instantaneous rate of change of input voltage Vn. That is whatever we have the differential voltage with respect to time, this is nothing but the rate of, this says that the rate of change of input voltage with respect to time, right? So this is what, so I can say there is an instantaneous rate of change of input voltage with respect to time, and it is also negative, and it is also directly proportional to the R and C values, that is the resistance value as well as the capacitance value. But when we go for the integrator, we know it is indirectly, that is it is directly proportional to the negative integral part of the input voltage, and it is inversely proportional to the resistance and capacitance values. But here in the differentiator, it is directly proportional to the instantaneous rate of change of input voltage with respect to time, and also it is equal to the resistance and the capacitance values. We call this as a constant values of R and C, right? So this is about the differentiator. So having look at having a brief just on differentiator, let us have a look on the problems. So we have a problem quoted as design an adder circuit using op-amp to obtain an output voltage of V0 is equal to minus of 0.1 V1 plus 0.5 V2 plus 2 V3, where V1, V2 and V3 are input voltages. Draw the circuit diagram. First, we are supposed to draw the circuit diagram, and then we are supposed to find out the constant values that are present in the circuit diagram. So first, let us solve this problem by writing the circuit diagram. So we already know from the equation, from the output voltage that is given, we can get the inference that whatever the summer circuit that is given is representing this as a inverting amplifier. So I have three voltages V1, V2 and V3, R1, R2, R3. This should be connected to the negative of the operational amplifier and positive of the amplifier. Now I have a feedback resistance RF with output voltage V0. So this is what is the circuit of the adders. This is what is the operational amplifier circuit for the adder with three different voltages to get connected together. Now we are supposed to find out the voltages V1, V2 and V3. With this, let us design an adder circuit. So this is what is a circuit diagram. Now let's find out what is V1, V2 and V3, right? Sorry, what is where V1, V2 are the input voltages. Draw the circuit diagram. So we have, let us find out, we have a standard expression for the adder circuit, that is for the inverting adder. We have minus of RF by R1 into V1 plus RF by R2 into V2 plus RF by R3 into V3. We know from the first expression RF by R1 is equal to 0.1 times of your V1, and similarly we have RF by R2 as equal to 0.5 and RF by R3 is equal to 2. We know when we resolve this expression, my R1 is equal to 10 times of your RF and my R2 is equal to 2 times of your RF and my R3 is equal to 0.5 times of my RF. Now if I assume my RF value as 1 kilo ohm, then I can say my R1 is equal to 10 kilo ohm and my RF is equal to R2 is equal to 2 kilo ohm and my R3 is equal to 0.5 into 1 kilo ohm, which is equal to 0.5 kilo ohm, which is equal to, just a second. So my R1 is equal to 10 kilo ohm, my R2 is equal to 2 kilo ohms and my R3 is equal to 0.5 ohm, right? So this is how we are going to design the operational amplifier to work as an inverting adder circuit, right? So by finding out the values of the different resistances that is present in the summer circuit, we can design an operational amplifier to work as a adder, inverting adder. Hope so. With this problem, these were these are all the references which we went through to prepare the content. Hope this video is informative to you. Thank you for watching.